Hello ladies and gentlemen, I am Dr. Claudia Albers, Planet X research and professional physicist, and today I'd like to bring to you another one of my articles. This one is entitled Einstein's Dream Realized, Unified Field Theory of Electrogravitation. Now, Einstein spent the last years of his life trying to unify his theory of gravity, the general theory of relativity, with electromagnetism, and it seems that he was not ever able to do so. Well, it is now possible to do just that, as the two interactions play off each other, and one cannot exist without the other. However, Einstein was right about one thing: gravity is related to space itself. This has to be the case because the position of objects in the universe has to be known instantaneously, and that is only possible if it is space itself that is interacting. Otherwise, it would take time for a planet to get the signal of where the star is that it orbits, and this would mean that all planetary systems would fall apart. Well, gravity is directly related to space because particles are related to space, and particles seem to be fluctuations or resonances of space itself, and so their position is known by every other particle in space instantaneously. So in this article, I'd like to explain as clearly as possible how the gravitational interaction works. Since the gravitational interaction is closely associated to the electrostatic interaction, I'll start with describing the electrostatic interaction. The particles which seem to be responsible for most of the structure we see around us and in the universe seem to be the proton, the electron, and the photon. So I'm going to mainly talk about those particles. The photon seems to be a carrier of both interactions and also to be a carrier of gravitational energy. And what we see illustrated here is the electrostatic interaction between protons and electrons, and the interaction is attractive between a proton and an electron. It is repulsive between two protons, and it's repulsive between two electrons. And this interaction is represented through a property that protons and electrons have been assigned, and that is charge. The proton has been given a charge of plus E and the electron minus E. The charge is of exactly the same magnitude because the interaction is the same in all of these three cases, but it has opposite sign. So protons and electrons interact according to the electrostatic interaction, and this interaction is of the same strength whether it is a proton and an electron, or an electron interacting, but it is attractive when we have a proton and an electron interacting. Now, this interaction can also be represented through a field or described through a field, and this field is generated by charged particles in the space surrounding them. So it's called an electric field, and it's represented by arrows, and the arrows point in the direction that a proton moving through the field would tend to move in. So in the case of a proton, its field is outwards, because if we place a proton close to it, this proton will be repulsed by this proton. So this proton would move outwards, and no matter where we place it, would tend to move away from this proton that is generating the field. So that means the field has to point outwards. Whilst with the electron, if we place a proton somewhere in this region of space, it would tend to move towards the electron because it's attracted to the electron. So that means the electric field has to point inwards. Now, the strength of the interaction decreases with distance, and this is represented by the distance between the field lines. And close to the charge, the field lines are close together, and that means that the field is strong there, but it's weaker further out because the distance between the field lines is greater. So that means that if the distance between the field lines increases, then the field is not constant, it decreases with distance. But it is possible to generate a constant field, and we do so by assembling lines of charge. So we can assemble a line of protons, which are all positively charged, and a line of electrons, which are all negatively charged. And then along this line, where the charges are, we have the same potential. It's electric potential. And so this is called an equipotential surface. And it's positive in the case of positive charges, and it's negative in the case of negative charges. Then what we have between the two lines of charge is a potential difference, and it's given by plus V naught minus V naught. So it's 2 V naught. And this potential then gives rise or can be written in terms of an electric field. So the electric field lines are always from positive to negative. So it starts at the proton and ends at the electron pointing downwards. But in this case, the field lines are parallel to each other, which tells us that the field is constant. They're always at the same distance from each other in between the two lines of charge. We can make the field stronger by placing more protons along this line of charge and more electrons along this line of charge. Then the fields are closer together, so the electric field here is stronger than the field there. But it's still constant because the lines are still parallel. And this idea of potential is very important. It is what causes a possible discharge between the plates, which would be like a lightning charge, if there's a breakdown between the two potentials. And this is what causes, because in the sun, the inner part of the sun is positively charged, so it has a positive potential, and then the outside is negatively charged. So there's a potential difference across, and that means that we can have discharges which lead to the sun producing light. Now the photon is a particle that moves at the speed of light and has no mass and no charge. But when it moves through a region of high enough electric field, it splits into two particles. And this is because particles are resonances. The photon can actually split into different particles of opposite charge and different masses. But if the two particles have the same mass, the resulting interaction is of equal strength, which causes them to quickly recombine back into a photon. But when the split happens and we get a proton and an electron, then the interaction in the three different cases that we get has different strengths, and the particles do not recombine back into photons. The two particles emerging from the photon therefore have charge and mass. The charge will be opposite but of the same magnitude on both particles, plus E and minus E, as I've described for the electrostatic interaction. And then both particles have mass, but both have positive mass. There is no negative mass, but the proton is a lot more massive than the electron. Its mass is about 1,840 times more massive than that of the electron. The energy of the photon is then transferred to the particles equally. The strength of the gravitational interaction between the two particles is dependent on the mass of the particles and on the energy each acquired from the photon. And we can see here an illustration of what happens. We have a photon moving through an electric field represented by the blue arrows. And if the electric field is strong enough, it will split into its constituent particles, the electron and the proton. But photons are quantized, that is, they have multiple possible energies which are integer multiples of a certain minimum energy. Thus, the energy of a photon increases in steps. And so if the minimum energy of a photon is E naught, then the photons will have energies E0, 2E0, 3E0, so on. And the photon transfers this energy to its two constituent particles. This energy has to be equally distributed, otherwise if the photon splits into a particle and an antiparticle pair, the interaction strengths would between the attracting and repulsing particles would be the same, and the particles would recombine into a photon again. So then we wouldn't get the structure of matter that we see in the universe. So the structure that we have in the universe results from the photon splitting into two particles of different mass, so that the interaction has different strengths. Now, the larger the energy transferred to each particle, the stronger the interaction between particles. The strength of the interaction can be understood in terms of a force, which will be proportional to the energy acquired by each of the particles multiplied by each other. So that's energy of what each particle acquired from the photon. And it has to be done this way because even though both particles initially acquire the same energy, once separated, one of these particles may acquire more energy by absorbing a photon, as I will show just now. So here's the gravitational interaction illustrated. So we have a proton and an electron. They repel each other. Two protons will strongly attract each other, so it's a much stronger interaction here, and two electrons will attract each other weakly. So this is the weakest of the three cases, the weakest interaction that we get. Now, the gravitational interaction causes protons to be strongly attractive and protons and electrons to be repulsive, and so on. So this means that the strength of the interaction is actually dependent on the mass of the particles, because the more mass of the particles interacting, the stronger the interaction. That becomes obvious. So that means that now the strength of the interaction represented by a force should actually be written as mass of the two interacting particles times the energy of the two interacting particles, all multiplied together. So if we have two protons interacting, then M1 would be MP, mass of the proton, and M2 would be MP as well, mass of the proton. So the strength of the interaction will be dependent on MP squared, or proportional to MP squared. And this sign here means proportional. We can also write a potential for each particle, in which case the potential would be proportional to the mass of that particle times the energy it acquired from the photon. And M can be either the mass of the proton, the electron. Then this the strength of the interaction is given by a force here, can be written in terms of the two gravitational potentials of the two interacting particles. If the field was not strong enough to split the photon, it may just cause the two particles inside it to move apart slightly. And this is illustrated here. And when this happens, some of the photon's energy is lost. What happens is it's redshifted. So when it loses energy, we get a redshift. But if there was, here in this case, there's not enough electric field to split the photon completely into its constituent particles. But when there is enough electric field and it does split into two particles, it's possible that the energy of the photon is not enough to give the interaction between the proton and the electron enough strength to be able to overcome the electrostatic attraction between the electron and the proton. So this would be a low energy photon, and in that case the two particles do appear, and they have the correct mass, but the electrostatic interaction causes them to combine and a neutron forms. So the gravitational interaction, the strongest part of the interaction is between two protons. And this causes protons to combine very strongly, to come very close to each other, and the strength of this interaction is the strongest when the particles are extremely close together, such as when they are in a nucleus. So this means that heavier nuclei can form, and we can even have some neutrons going in there, and this is basically fusion occurring. Now, this interaction between protons is so strong that even though we may have a neutron which has an electron in there, and this electron will be repulsed by the other protons, the interaction between proton and proton is so strong that we can end up having some neutrons in the nucleus. However, even so, sometimes we have electrons leaving the nucleus where a neutron then turns back into a proton. And this is called beta decay. And this is because the proton and the electron tend to be separated by the gravitational interaction. They tend to basically fly apart. Then we also have atoms forming, and atoms are made up of protons in the nucleus. There may be some neutrons as well, but the charge of the nucleus, and therefore the atom, is defined by the protons, because the neutron has no charge, because it's plus E from the proton plus minus E from the electron. That means zero charge. So in this case we have 3 protons, so that would be the nucleus that we have formed here, a 3 proton nucleus, and then it would have it may have 3 electrons, and the electrons are outside the nucleus, actually quite far outside the nucleus, and they are outside the nucleus because there are 2 forces acting on it. And in this illustration I use the green arrows to represent the gravitational interaction, and the orange arrow to represent the electrostatic interaction. So this electron is repulsed by the protons in the nucleus, and so the green arrow points outwards, but it's attracted to the protons through the electrostatic interaction. And wherever the 2 interactions are in balance, that's where the protons would be. And that means they are trapped in a region outside the nucleus, in a region where the 2 interactions are in balance. So now, the electrons can also gain energy by absorbing a photon. They gain gravitational energy by absorbing a photon. And when they do, that means that the interaction between this electron, the gravitational interaction between this electron and this proton increases. Because it now has more gravitational energy. And when that increases, and since it's a repulsive interaction, the electron will either leave the nucleus, or it will move up into an orbit that's further out from the nucleus. And so larger objects, celestial objects, astronomical objects, are all made out of protons and electrons, and even smaller objects, planets, and even smaller objects on the surface of the Earth. These are all made out of protons and electrons. But basically I like to concentrate on celestial bodies. These will have an overall gravitational potential, which is obtained by adding up the potential of each particle inside the object. And gravitational potential is different from electrostatic potential in that it is always positive. And this is because mass is always positive, whilst with electrostatic potential we have charge, which occurs in 2 opposite signs. Now, due to the very strong attraction between protons, the gravitational interaction causes less heavy nuclei to gather around the heaviest or denser in protons nuclei, so that any astronomical object will have the highest density of protons in the atoms found at its center. This means that the matter at the center has the maximum positive gravitational potential. Matter less dense in protons will gather around the inner core of very dense matter. Electrons, which are part of the atoms in the matter in the interior, repelled, and especially outer electrons are stripped from these atoms and forced to move outside of the body and thus form an outer layer of electrons. The object therefore becomes a superatom or a macroscopic atom. Because the inner core is made of matter which has the highest density of protons, the core has the highest gravitational potential density, and the gravitational potential density decreases as we move through the different layers towards the surface. So in the case of the Sun, the gravitational potential density of the Sun decreases as we move away from the center of the object. So it will decrease as we move from the core of the Sun outwards towards the surface. But even the rings making up the solar capacitor also obey this rule. So the outermost ring in the solar capacitor is the region with the least gravitational potential density. And so this will have basically the least potential. And as we move inwards, the potential density of the particles in the rings increases. So this is also why the lightest nuclei are found in the outermost ring and the heaviest nuclei are found in the innermost ring. Now, because electrons have a negative electrostatic potential and the atoms at the center of the body have been stripped of electrons and are now positive ions, there is now an electrostatic potential difference between the inside and the outside of the body. This electrostatic potential will give rise to electric discharges, and when they are frequent enough will allow a star to give off light. And this is what we see here. So the different layers here are, so we have the densest matter in the center, and then as we move from layer to layer we get less and less dense matter, and therefore the gravitational potential decreasing as we move outwards, but it's always positive. But the electrostatic potential is positive, and that's the largest we can get. It's right at the center where we have the most positive ions, because that's where we get the strongest separation or repulsion, gravitational repulsion between protons and electrons. So the most electrons, this is where most of the electrons forced to leave atoms will come from and go to the outermost layer. So you get the most positive ions here, so the greatest electrostatic potential right at the center, and then the electrons that form here will have negative potential, and so we have a potential difference between the interior and the outer layer of the object. And this means that we have a superatom. It's like a nucleus inside and electrons on the outside. Now the proton-proton gravitational attraction is not as strong at medium or long distances as at short distances, but it is still strong enough to attract celestial bodies. Two celestial bodies, and that is a star, planet, or a star and a planet, or two planets, attract each other because their cores are very dense in protons, and these protons attract each other due to the gravitational interaction. The cores are also positively charged, as the atoms in the cores have lost electrons, which form the outer negative layer of the electrons. And so the electrostatic interaction causes the ions in the interiors and the electrons in the outer layers of both objects to repel. This repulsion is not as strong as the gravitational attraction between protons. Nevertheless, the repulsion between protons and electrons, and that is the electrostatic repulsion, cancel some of the gravitational attraction between protons. So the overall attraction seems to be quite weak. This is why you often hear that the gravitational interaction is a weak interaction. And that is just because some of the forces are canceling. So what we have here is two objects. So they have a dense interior, and the gravitational interaction between the two rich in proton cores or interiors of the objects will cause a strong attraction. We also have a repulsion between the protons in one of the objects and the electrons in the other, and that will cancel some of this attraction. But I have just inbuilt it into this green arrow, which represents the overall gravitational attraction between the protons that causes these two bodies to attract. Then there will be electrostatic repulsion between the protons, or actually the ions, in the interior of both objects, and the electrons in the outer layer. And the two I've combined in the orange arrow. Then we have to add the two interactions together, and we get this resultant interaction, which points to the other object, so it's attractive. So we get an overall attractive interaction, and this is what we have been told is that weak gravitational interaction that we've all been taught about. But it's actually the combination of the two interactions, the gravitational and the electrostatic. Now, when the two objects come so close together that their outer layers start to overlap, what happens is they are closer together, these electrons and protons from the other object. So the repulsion, the gravitational repulsion between these two increases. And then that increase in that repulsion plus the electrostatic repulsion may be enough to then cause the resultant interaction to be repulsive. So the two objects will move apart. And then we can also represent the gravitational interaction through the field, the gravitational field. But in this case, the field is not of the same strength for both particles. It's stronger for the proton. So what we have is more field lines. It's inwards, because if we put a proton close to this proton generating the field, it will tend to move inwards towards the proton because it's an attractive interaction. So the gravitational field for a proton is inwards. The arrow points inwards, and it's the opposite for the electron, because a proton will be repulsed by the electron. It will tend to move outwards, so the field lines point outwards. Again, I use green arrows because this is for the gravitational field. So in conclusion, the gravitational interaction is a charge separation interaction which causes positively and negatively charged particles to exist in separate layers. The interaction becomes the strong force in the nucleus and causes all objects to have proton-dense interiors which attract each other. The photon is the carrier of both the particles that make up matter, namely the proton and the electron, and also the interactions which result in the observed structure and energy transformation mechanisms we observe in the universe, including a star's ability to produce light. In addition, the photon is a carrier of gravitational potential energy. And I'd like to end again by thanking my Lord and Savior Jesus Christ for revealing this mystery and the truth to me. And in addition, I'd like to urge anybody who does not know him to start getting to know him. He died so that our sins can be forgiven. So we should start by asking him to forgive us for our sins, and then to ask him to take over our lives and guide us. It will be the best decision I believe any of us can ever make. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.